I know, the Vera C. Rubin Observatory. I won't shut up about it. Well, here we are. Now, this incredible observatory has its camera installed, its primary, tertiary mirror, its secondary mirror. It is a fully operational telescope. And now it is in the commissioning phase, moving towards first light, which we should see by the end of the year. And when it does come online, it is going to find millions of supernova, billions of galaxies and stars, and show us all of the things the universe was doing when we weren't looking. It's going to be a fire hose of astronomical data. And to help put this all in place and give me perspective, I've gone right to the top to Dr. Edward Ajhar. He is the program director of the Vera Rubin Observatory, which is a collaboration between the National Science Foundation and the U.S. Department of Energy. And we talk about the current state of Vera Rubin. We talk about the sort of larger science objectives and then how we should be able to see this program unfold over the next coming months. And so if you're excited about this observatory like I am, I think you're going to find this interview instrumental in helping you put everything into perspective. All right, enjoy this fascinating conversation with Dr. Edward Ajhar. Edward, my audience is very familiar with Vera Rubin. I've been talking about it nonstop, but give us a status update. How is the observatory doing? Where are you at right now?
Well, we're at an extremely exciting moment, really. They just got the camera installed on the telescope very recently and began on-sky engineering work just last week. So internally, a big celebration, right? You'll get to see more eventually. All those things will come out, and then now they have weekly sort of updates going out to the science community, so they know where they're at. So it's very exciting. They're making images with the camera on the sky and getting things tuned up and optimizing the telescope. So it's very exciting. I know I talk to the project people regularly, so it's so much fun to see what they're doing. And so we can't wait to show you pictures. We're getting close to that. So they're trying to get. So that's their focus now. It's a little bit of a tension, right? You got to get all the engineering stuff going, and everyone wants to get it, and everyone's very excited to make the images and show the public what they're doing. So it's exciting time.
And so, I mean, we followed the installation of the primary mirror, the primary tertiary mirror, the secondary mirror, as well as the camera. That feels like the big to-do list is complete. So are there any more bits and pieces that have to be installed, or are we just moving into commissioning now?
Well, we're heavily into commissioning now, and there's really no more major components to do. I mean, there's always a few things to fix up and to finish up. Some components on the dome have to be completed, but all of that's going well. So all our major pieces are in place. We can't wait to start closing out the construction and moving on, at the operations team take over. So that's what we're aiming to do at this point.
And so give me a sense then, of like what kinds of tests people are doing right now in terms of the commissioning phase and how we sort of think this is going to roll out over the next couple of months.
Well, as you know, it's a very complicated system, as most modern things are. So what they're focused on, having all this complex equipment work together, right? There's all kinds of safety things in there to protect the mirror, protect the camera. And so one of the things you have to do right now with the camera is to make sure the active optics are working, right? It keeps the mirror in the right shape. And as you move the telescope, right, it's got to keep all these shapes, and and you're moving things. You want to get that moving faster and faster. So those are the kinds of things they're working on, making sure that as you're observing, the optics are actively being sharpened to get the best images you can. And as you move from one field to the next, do that. So those are the kinds of things they're working on tuning up and getting that better and better. And the results so far have been great. It's the kind of thing
you've seen some pictures.
I have seen a little bit of pictures. Yep. They share it with me a little bit, so it's great. But I kind of, as a scientist, you don't need to see the picture to understand what's going on. So they're getting great, uniformity across this huge field of view. Right, those are the kinds of things I'm looking at. And then there's things like light that's inside the dome that's coming in and those types of things that getting the calibration screens, all lined up and getting those things ready so that you get the whole focal plane calibrated well. So those are the things that are necessary not only for the science, but when you're trying to make pretty pictures, you got to get those things in place too. So those are the things they're tuning up right now. It's all the normal kinds of things that happen.
And then the other half of this is the data, which is, it's got to just be a monster of a project. So where is that side of things at?
It's amazingly in a great place. I mean, I don't know how else to say it. They're an extremely impressive team. They are modern software engineers. They are modern scientists and working with the software engineers. So that team you couldn't have a better team, to be honest with you. I mean, just this week, I saw already, light curves of variable stars coming out. I was like, well, we're talking about 1 week, they're on the sky, and they're already doing that. So those kinds of, those kinds of things are happening. So they're tuning up the whole network, right? It has to go from South America all the way up to Stanford in no time. So NSF and DOE, National Science Foundation, U.S. Department of Energy have teamed up on this whole project. And so they are the ones who are really funded through the Department of Energy at the SLAC National Accelerator Laboratory. They're the ones that's where the U.S. data facility is. So the data go there, and that's where all the initial processing takes place. And so, those images have to make it within 7 seconds. That's pretty much their goal. So it's kind of amazing, right? We're talking about 3,200 megapixels, right? And they're being sent across all continents in 7 seconds, and then processed. The idea is the data need to be processed within a minute, right? So that's very fast. And so it takes quite a team on every way. The network has to be great. The programming has to be great. The protocols being chosen at every level in the software, and all the technical, they have to have the code written, right? It can't be, oh, this is still not working. If we were in that place now, it would be really bad. But it's just the opposite. They're in a great place.
Yeah, it's like redirecting the Amazon once it's already, started flowing.
Yeah.
And that's interesting to me, that sort of decision to house the data back in the US as opposed to on site. That sounds, that's challenging, right? That's all bandwidth, not
it sure is.
Storage.
Yeah, they were planning, for years, right? For years, building the network in South America, and in the U.S., we have a lot of network for fast transfer. I guess, especially Department of Energy has. So we're using their network essentially when it gets to the U.S. And before that, the National Science Foundation really funded a lot of the network that's available in South America to get that all up to speed. And then there's a lot of private companies that all have worked together to make the network work well. So yeah. There's interesting stories everywhere here, the science, the technical, and the education things, which I'm sure we'll have a chance to chat about that too at some point.
Yeah, so let's, this is that was the update, I think, for the people who've been following the story quite carefully, and sort of, hopefully that'll give them a certain amount of confidence that everything is moving and that they'll be able to see those pictures and that data and, those data really soon. So let's go back and give people a sense then, who aren't as familiar with the observatory, give us a sense of the technical capability of Vera Rubin and LSST.
Yes, excellent. So data get to the U.S. data facility right within seconds, and immediately, the first thing that the observatory has to do is build a template of the whole sky in the southern hemisphere, right? So once you have that template in place, which is basically built by imaging the whole southern sky, once that's in place, then you take your most recent image and you take a difference from the template, right? And so that difference then allows you to find the difference image allows you to find something that's changed, variable stars, supernovae, asteroids, all the kinds of things that some of the things that you're familiar with, of course, and so that capability is really critical, because when you can do it within 60 seconds like that, then they're going to send out alerts, and those alerts. So this alert stream will go out to alert brokers, right? It's a very interesting network that gets built. These alert brokers will then be available to scientists around the world to say, okay, I'm interested in this type of event, this type of star, and this kind of thing. And they'll be able to just pick out the things that are interesting. And then follow-up observations can occur around the world. So if there's something interesting that happens, we'll be able to follow it from the time Rubin sees it, within a couple of minutes, to say, okay, we got other observatories can now lock onto those objects and start observing them. And you can do this around the world then, right? As the Earth turns, right, that nighttime comes up as the day progresses, and you can be able to follow things. So this is a new thing, to be able to do that and to build this network around the world for follow-up observations. So very excited about that. We call that a time domain, right? And it's not really new to astronomy, but to be able to do it where you have up to 10 million alerts a night, it's
10 million alerts a night.
Alerts a night. And of course, you're not going to follow up on all of those things, but so that's a very exciting thing, is who knows what interesting things we have yet to discover that we're going to want to follow up on. And, you've heard of gravitational waves. And so that's another thing that this instrument is capable of doing. So if there's a gravitational wave event, then we'll be able to scan the sky in that area and get a pretty quick survey of something. And so it'll be very exciting if we can follow up on something like that quickly. That's challenging, right? But it's the kind of thing where the survey can be interrupted to some extent, and the normal cadence, and say, okay, let's spend a little time over here and look for the gravitational wave event that could be happening. So that's kind of the fast part of it, right? The things that are going to happen. The asteroids and those things are more of a daily kind of cadence. Every day, you'll look for things that that have orbits that we can start tracking, and those will get fed into the Minor Planet Center on a daily basis. And then the other part that's I don't want to say unique, but given the scale of this, it's certainly very special. Rubin is going to be able to will map the whole sky, and each year, and then every year there'll be a big release of data, both the images and the catalog of objects. And the images, right, are going to be taking your whole year's worth, or all the data you have to that date. You'll redo this every year of all the data that you've collected, and you'll have a really deeper and deeper and deeper images of the whole southern sky every year with these releases. And the catalog, they get reproduced, right, and they get better quality. It'll get fainter each year, and so that's the other thing that's going to be just a treasure trove of data for so many things. So, yeah, the solar system, yes, it's going to find all these, millions of asteroids, and it'll find comets, and so that's very exciting. And you've already talked about the whole Planet 9 thing. So if your audience is familiar with that, but on the other end of things, the galaxies, the stuff further away, we're going to have quite the map of our universe. It's going to find around 20 billion galaxies will be cataloged, right? It's mind-blowing number, 20 billion galaxies. And this instrument has 6 filters, right, going from what we call the U band, right, which is sort of near ultraviolet, all the way to into the near infrared band. So up to the Y filter. It's for the astronomers listening to this who don't already know, right? So we have those 6 bands. And it's incredible that we've got CCDs, the detectors that can detect things across that broader spectrum to the depth that they're going to do. And to have them, of course, we have so many scientists working on this, and all the funding will pay for all the scientists to do all the calibration, the photometric calibration across those 6 bands. It's going to be incredible to have that kind of consistency that'll be across the entire sky. That's hard to do if you're just an individual astronomer trying to do that. But we're going to have the whole sky done that way. And so you'll have colors of all these galaxies, colors of all the stars. There'll be about 17 billion stars cataloged with this. So we will be doing the galaxies. So if you're an extragalactic astronomer and you're interested in that, you'll have all those data for that. And if you're a galactic astronomer and really want to study the stars, this is going to go across the whole galaxy and to pretty faint magnitude. So it's going to be incredibly fascinating a time when the data start coming out. And so for years, this will be just an incredible legacy, and it's appropriately named that way.
So it's kind of an interesting time. I mean, there are these grand mysteries in astronomy. What is the nature of dark matter? What is the nature of dark energy? And all of these instruments designed to help solve this problem have all shown up at the same time. We've got the Euclid mission, we've got the DESI survey, we've got the SphereX mission just launched, Nancy Grace Roman is in the wings, and now Vera Rubin is coming online. Like 5, I'm sure there's more that I haven't even thought of here. They're all going to come together. And so what role, and I guess like what perspective do you think astronomers, say 2-3 years down the road, once they've been able to start to digest all of these data from all these different instruments, what kinds of answers do you think they're going to be able to start getting about those big fundamental questions?
Well, that's what makes it all exciting. The thing is, what do we really understand? Every time the more we study our universe, galaxies are getting discovered earlier and earlier and earlier, and it's really a puzzle how they form so fast, right? We start out with a Big Bang, a very smooth, incredibly smooth universe, and before you know it, like within a billion years, we've got we have galaxies forming with a lot of structure, and it's hard for us to understand how that's going to happen, how it really happened. So the more that we understand about some of the fundamental physics, how dark matter plays in that process, and how the dark energy plays, and DOE just recently had an interesting result come out from DESI, and so it's suggesting more and more that dark energy is changing over time in the universe. And if that's happening, right, that will play into how galaxies form, how they evolved over time. And when you have the statistical power of a survey of this size, what we'll learn about it will be, it's an opportunity again to really grasp what's going on. So you can tie all the images that we see to these great redshift surveys and start putting the pieces together. And as you mentioned, things like Roman, that from the space that will hit on the more on the infrared end of things. So you can tie what we see with Rubin to what we'll see with the Roman thing, and so because there's carefully planned overlap of the two surveys there to make sure that we have the depth of that. And so that's how you kind of can connect what you find from the smaller survey, but different kind of survey, to what we're doing with Rubin. So yeah, it'll be an incredible thing to really try to understand how the universe really started from that Big Bang, started forming galaxies, and how they evolved to where we are today. And there's a lot of unanswered questions in every part of it. And I haven't gone into the stellar thing mostly because I'm extragalactic and my but the stellar. There's going to be things that we don't understand. There's always things we don't understand about stars, and to have the monitor that we'll have now, this time domain monitor, all these variable stars. There are some stars that have very long periods, that aren't so easy to get telescope time to try to do that. But this is all going to come out of the Rubin, time-lapse survey that it's going to do for 10 years. So looking at the whole sky twice a week, for 10 years is just going to be an incredible movie. And so it's going to hit every area of astronomy like no other project has ever done.
I rattle off often in my videos like the numbers of stars in the galaxy and the number of galaxies in the universe, and they're enormous numbers. But like the Gaia mission gave us really detailed information on 1 billion stars, 2 billion stars. Maybe, we'll end up with a fairly large number of stars. But you said 17 billion.
About 17 billion, yeah.
That's crazy. Yeah.
Yeah, once you start getting fainter, right? I think Gaia went to 22nd magnitude or somewhere in that neighborhood. We're talking here that this one will be going down like a 27th magnitude, right? So it's that much, 5 more magnitudes is a big leap. So that just cranks those numbers up. And what usually happens when we find numbers and we go to fainter levels than we had done before, we just start finding things we've never seen before. And and then instead of a few, is it a fluke? What is this thing? Then you'll have a whole lot more. And so you'll have a good collection of things we've probably never seen before, and you can start understanding what's really there. Because to have this kind of monitoring of the whole sky is going to just be revealing. That's very exciting part. One of the many exciting parts.
Yeah. And so for you as an extragalactic astronomer, back to this idea of dark energy, there are sort of like these two main ways that people are measuring the amount of dark energy that's in the universe. You've got whatever's the consistency in the cosmic microwave background, but the gold standard really is this sort of expansion of the universe, the large scale structure of the universe, looking at those type 1a supernovae. And I know that up until this point, astronomers only know of about 2,000, 2,500 of these type 1a supernovae. Give us a sense of how many type 1a supernovae you're hoping to see with Rubin over its main mission.
Yeah, we're going to be jumping to millions on that.
Millions,
right?
Yeah.
Yeah, I don't know what the exact count is, but it's millions. Maybe it's as many as 10 million. It's a lot. So so those will be coming out regularly, right? So we're going to have lots of that. So that's one of the ways that we attack the dark energy question, right? Because with millions of supernovae, you really will build out that how things have evolved, that they're evolving, and we can see it there. So that'll be refining the dark energy measurement just from that. The other thing we're going to be doing with dark energy, because we're going to have these billions of stars, right? 20 billion galaxies, right? Those galaxy shapes, right? How they change over the whole sky is another measure that we have for understanding dark matter and dark energy in the universe. And so those subtle things are one of the drive the technical capabilities of the camera, the instrument, how carefully we have to calibrate the data, how carefully we have to be with the data. But that's going to be another measure of the dark energy and dark matter in the universe, is to see how they affect the shapes of the galaxies across the sky statistically. So
and so, could you be actually mapping out the shape of galaxies based on where the type 1a supernovae are going off in these galaxies, or finding galaxies you didn't know were there because you assumed that there has to be one for the type, because they're so bright, right?
Yeah, they're very bright. Well, you'll see the galaxy, in most cases where they're coming from. So that's not going to tell you so much about the shape, but we're going to see the shapes of these galaxies, right? So that's that, and across, again, the statistics that's going to provide across the sky is just another way that we learn we're learning about dark energy from the supernovae just by their distances, right? That's essentially how far away they are, because we're using that as a measure of distance. The other thing, which is basically independent, that's what makes it exciting, right? Forget about the supernovae and their attachment to galaxies. Just the galaxies themselves, having this kind of sample uniformly done across the sky, is going to teach us about how are those shapes being changed. How are they being lensed? I mean, we're talking about weak lensing is the technical thing we call it, right? The weak gravitational lensing affects the shapes of these. How we see the shapes of those galaxies. And so statistically looking at that is how we will learn about additional things about dark matter and dark energy.
Right. And so, but then speaking of strong gravitational lenses, you're going to find those too.
Find lots and lots of those. Yeah, I don't think I have a number.
I reported on this, but I forget. It was a ludicrous number, right? Millions or something like that.
I'm sure it's going to be a lot, because it's all there, right? It's all there for the finding. I have to tell you, when I came back to National Science Foundation as a federal employee in 2016, I got put on this as working on this project at that point, and so I started reading in detail the whole science book, right? And you can still find the science book. It's great. And one of the things there's many things that got me very excited. Of course, I had known this was going on, but you start digging into details. I honestly say I was disappointed. Why aren't we building one in the north too? Because we're only going to get, about half the sky. I want the other. Yeah. I want a little bit more.
That question is coming, but feel free to jump to it. Yeah.
Yeah. And it's so I'm, you're certainly wishing for that, because it's going to be such a treasure trove. I mean, these are the science obvious things, right, that are all listed, the science pillars that we're hitting on. But there's so much, just having those images all calibrated and all the bands. It's hard to imagine anyone doing a paper on any particular object that isn't going to pull them out and look at them and have those, at least in the paper, to show what's going on. So you have a visual to go with it. So that's going to be there, that whole legacy. And then you're going to just wish that you had that northern hemisphere, but it's still going to be incredible. Don't get me wrong. It's just, wow. the rest of the catalog is sort of incomplete. The catalog will be incomplete without the whole sky.
So, I mean, I'm sure this conversation has been had many times, which is if we did do a Northern Hemisphere one, how cool would that be? And again, I know that nobody has agreed to this. Nobody's decided this. No one's even put this into any kind of document or anything. But, do you think that it would be better to have like a mirror of the Southern Hemisphere, or actually then build the next generation and kind of leapfrog as the next step?
Yeah, I mean, that's the great thing. I can always speculate.
Just put your speculation hat on. No one's listening to this. Don't worry about it.
Right. No, the thing is, the science drives it in the end. So whatever people are thinking before you start this survey, it's going to evolve, and probably within the first few years. I mean, that's the other exciting thing about science. In the first few years, we're going to learn new things that we haven't even didn't realize would come out of this, and that will drive a lot of things. It could even disrupt the cadence, right? The cadence that's planned for the survey, because you might say, well, look, this is too important. We're going to have to follow. So there will always be that kind of tension, and it makes it very exciting. And it's also been one of the exciting things about working on this project. The community has been heavily involved all the time. It's not just the project people; it is the whole community that's been contributing, and not with any hesitation to tell us what they think about what the cadence should be. For example, because do you look at the same patch of sky twice a night or 3 times a night? Makes a big difference and it affects all the science, right? And certain things really want you to do one thing, and other things that really want you not to do that. And so there's that tension. It's a very healthy thing, and the project has been really excellent about trying to make minimize the complaining, if you want to think of it that way, or minimize the unhappiness, so that you're really optimizing the science you get out of it. But as soon as you throw a curveball in, and there's some unknown thing that no one had planned, who knows what that will do. Everyone might get behind, oh, this is too important, we have to follow up, we have to change and do things a little differently for those new things.
And are there plans to do that cadence? Like I think about, say, places like the plane of the ecliptic, places where all the asteroids are. Maybe that makes more sense to hit that more regularly, or is it still just going to be an equal cadence for the entire sky?
I would hardly call it equal. There's some interesting images you can find showing how the cadence will play, because you're not going to spend quite as much time in the galaxy simply because there's places where it's very dusty, and you're just not. It's just kind of like not the best place to do it. So it is optimized in a very interesting way, and it keeps evolving. Over the last 5 years, especially, it's evolved a lot. It was much simpler before, and now it's it's a very sophisticated cadence. I would put it that way.
Right. That's interesting. So you could see the algorithm evolving to match what seems to be the science case, and then as it turns out we find out an entirely new class of objects that is incredibly exciting, they may change the algorithm.
Who knows?
More. Yeah.
You never know, right? Because it might not be a big tweak. Who knows what it's going to be? Like I said, those are the things you kind of look forward to, the unknown things. My first exposure to doing any kind of real astronomy, I was in high school, right? And so it was a summer program called the Summer Science Program, still exists. And, one of the things we did was to determine the orbit of a known asteroid, right? But you had to, take data with photographic glass plates, and you had to get at least 3 observations to figure out the orbit of this asteroid. But in the process of doing that, you use what was the Palomar Sky Survey, and that sky survey, was on big Polaroid, not Polaroid, but big prints, big size prints. And so you would do that, and you would take Polaroids of a subsection of that as a finding chart. So when you're observing, you go find it. So every astronomer, certainly in my time, knows that Palomar Sky Survey. And it's not like it was particularly great, but it was the whole sky, right? So it's, and so you have the whole sky. And what is this going to be? This is going to be a whole sky, well, just the southern sky, but the whole southern sky mapped in 3 different bands of visual bands, and it's going to be a highly well calibrated, awesome data across the sky. So what a legacy it's going to be. And I say that because it won't be used as finding charts. I mean, that's one of the things you could use it for, but you're going to use it to be able to learn so much from it. So again, there's the catalog. You got those things you can study, galaxies. But when you are interested in just say a few hundred galaxies to do a particular study, the data are already going to be there for you, and you're going to be able to analyze those galaxies. You just think of a random galaxy in a nearby cluster, like in the Virgo cluster. Well, I did a lot of work like that, and those data are going to be there free of charge. And the project's not going to do anything with those particular galaxies. I mean, they're going to do some basic measurements on it, but now you can fit that galaxy. If you take, you cut out this from the survey, you cut it out, you fit and subtract that galaxy. You're going to be able to look at the globular clusters in that galaxy. This was something that you had to get telescope time, a lot of telescope time to do, and now it's all going to come free of charge. And so there's a lot of stuff that's never been observed that we're going to get out of this, again, free of charge. That isn't really a part of the plan. It's not part of the catalog, but it's a lot of things like that are going to be done across all areas of astronomy. So anyway, I keep diverting, but there's so many.
Yeah, no, it's fine. It's fine. Are you kidding? That's great. But yeah, like philosophically, I'm really excited about surveys in general because of that thing that you just described, which is that I think, in the olden days, you would book time on a telescope. You would then observe your object for the amount of time that you were allocated, and then you would take your data and you would crunch it down and you do whatever you needed to do. And if you then had a question about, oh, this reminds me of some other object, well, that's just too bad. Right. But now we're in this world where somebody was kind enough to take a picture of everything all the time at a level of depth that if you do have those kinds of questions or you're looking for larger patterns, you can now go and pull them all because someone took a picture of that galaxy every 3 days for the last 10 years.
That's right.
And that's what that's what makes me so excited about Gaia, but also about other survey instruments. And I feel like there's an entirely new kind of astronomy that has been evolving over the last couple of years because of this access. There are astronomers out there that I'm sure watching this that have never bothered to pull data from a telescope because there are these surveys out there.
I mean, it'll be exciting. And we've talked about the time domain going in one direction, right? Well, you see a supernova and you track it afterward. Well, you can also look at what's happening right before things, right? Because you have the history, not just this is interesting, let's track it. We also have the history from the previous observations that we've got. So, and depending on when the event of interest happens, right, you have a long history of to look at the stars and see what's happened. So yeah, it's going to be very exciting. And
there are actually a couple of specific examples that I was thinking about. For example, like when a star goes supernova, it's always been really tricky to find the precursor star to that supernova. And so now I guess in theory, what kind of a window, let's say that you want to catch a supernova the moment it's going off and you're willing to watch all the stars, all the supernovae, and then try to get that one the moment that it's going off. Will we be able to find those?
Well, once you still have 10 million or so supernovae, maybe you'll get some, right, that'll be just close to the time that the supernova goes off. So I think there's going to be interesting things like that are going to happen. The problem with a lot of supernovae, of course, they're in a galaxy that's far enough away that you really don't have much resolution. So you just have the brightness. And so unless they're occurring out far enough in the galaxy that you might have a chance of getting something, mostly these things are going to be blended with other stars and whatever else is out there. So I don't think we're going to have an isolated one like that, but hey, you never know. It's a big universe.
Yeah. So, and then what are some things? I mean, I always sort of describe this as that it's all the things that the universe is doing when we weren't looking. And now we're going to look, and now we're going to watch. And what are some kinds of things that you think, we have these faintest hints of right now today, but now we're suddenly going to be able to build a much better idea that they're happening, very rare events?
Well, that's a really great question. I don't know that I have any great answers for you. I will suggest that, there's boring things or seemingly boring things. I mean, supernova, everyone is excited about that because it's an explosion. It, could become a black hole, neutron star or something, or it's just total annihilation of the star. But, you think about all the regular stars like ours, right? And we're going to be able to monitor them like we've never done before in our own galaxy, our stars. So all these stars are evolving, right? They're all burning and burning their hydrogen, and there's other stages too that we can monitor like we've never really been able to monitor in such large numbers. So I think there's a lot to be excited along those. Even though it doesn't sound exciting, there's always subtleties that we didn't understand, and the more we understand the physics behind stars like that, the better we really understand how galaxies evolve. Because if you don't really understand what's going on with the stars, it's hard to really say how the galaxies are going to evolve too. So I think there's a lot of interesting stories there that we don't understand and haven't really been able to monitor. So as I mean, it's not like we don't know anything, but we're going to have more data that we ever had before, and those are the seemingly more mundane things. And one of the beautiful things about science is people always have different interests in different areas. So I think it's going to be a treasure trove in that area too. And I would say the less obvious time domain things of interest, or maybe less obvious to a lot of people. So I think that's good, but I always come back to, well, what are we not expecting, right? Because it's the other thing about the cadence. You don't want the cadence to like eliminate things just because you don't think that's an interesting object. So they did a great job in the cadence figuring out, okay, let's make sure we cover the whole kind of space of time, and we won't eliminate things just for our cadence for the known science. So I keep going back to the unknowns. Those are going to be where a lot of I can imagine a lot of interest.
Yeah, I mean, like there are fairly recent phenomena. I think about things like, say, tidal disruption events, where you've got some star that's being gobbled up by a supermassive black hole halfway across the universe, or fast radio bursts that, I think we've only known about these since 2007. And it just happened to be that someone captured this brief flash of radio waves. And it's kind of hard to predict what we don't know yet. So only by watching everything will we start to find these new events. And then I guess people will have to try and figure out what caused them. And then, we're off to the races.
Yeah. And I think that those are the things that can be very interesting, because it could be just by having this much data, right? If there are things that vary more than we think, maybe we'll see that. Or I think there are things that people probably have not investigated enough because you can't really collect enough data. And now there will be a lot more. So,
yeah. And then back to this conversation about asteroids, objects here in the solar system. Give us a sense of like how many near Earth objects, even just asteroids in the solar system, we're aware of, and how many can we hope to find?
Yeah, that's getting further away from my expertise. But no, I think it's going to be millions. I mean, it's really going to it's like a million or so asteroids. We're going to clean up, right? In the first couple of years, we're going to find these things. So it will be an early and interesting story for Rubin, and it's just funny. What we a lot of times what we know in astronomy depends on how bright something is, because if they're faint, even if they're close by, we don't know too much. It's almost like in the ocean, right? Where there's a lot we don't know about the ocean, because it's not too easy to get down and look deep, and it's a huge ocean on our planet, so we don't get a chance to investigate it much, even though it's right here. And it's almost the same kind of thing in the solar system, right? You've got so much here, so much detail, and it really is. The more we understand about our solar system, the more we unlock about how it was formed. And so, but it's because there are a lot of faint things, and it's a big sky again, because it's nearby. You have to look at a whole lot of the sky in order to find them. So we know those are freebies, right? And that's where, the Planet 9 or whatever it is, there could be other things that to explain the gravitational effects we see by all these other objects. When we start inventorying them better, it's going to reveal some new things. I'm sure that's going to be another interesting thing in the next couple of years. So, asteroids and comets, they take a big part of. They're a big part of what our whole solar system is. When we study the solar system as a whole, so we just have a lot to learn because they're faint. Right? They're faint objects, and that's what this will really Rubin will really help to uncover.
Yeah, and you described this earlier on, that you will be submitting all of these objects to the Minor Planet Center, and I think it's a good way to approach. I forget the number. I think it's 9 times as many objects than the rest of the astronomical community combined. I can just imagine Vera Rubin showing up every day with a big pug. I found these.
Yeah, no, it's going to be. Well, they've been preparing for this for years with the Rubin team to be ready to accept the incoming reports. So they're geared up and ready to go because it's just going to be a huge volume. So and what will happen is as they feed each day feed in new observations to the Minor Planet Center. When it's a new discovery, it goes in, it'll get tagged and labeled, however they do those things. And then they'll have a new catalog each day too. And so the new catalog will be fed back into Rubin each day, and they'll be using that to add observations of things that are known. And then of course there'll be new discoveries, and those will come back in. And so that'll be a very exciting couple of years, first few years, especially as they discover new things, and the Minor Planet Center is building up this much bigger catalog now of asteroids and objects.
Yeah. One of the things I've been sort of thinking would be fun is once it does go online to do a live stream with a bunch of astronomers and sort of watch as the various live notifications come out. And then you're like, oh, supernova, oh, asteroid, oh. Do you think that there will there be ways for the public to be able to engage with those data as they're being shared, as opposed to just astronomers?
I expect there will be something like that because what the project is funded to do is to produce these, like I said, this alerts called an alert stream, and as I said, about 10 million events. It won't be that immediately, but eventually it'll be about 10 million events per night estimated, and it's going to go out to 7 different brokers. So the project is basically going to send the alert stream out, and then they're basically done with it because it's beyond what they really can do. So then the alert brokers become very interesting, and one of NSF's facilities, Noir Lab, will be one of the alert brokers, and and it'll at that point, it's a kind of thing where you'll be able to query. I'm interested in this sort of thing. So if you're interested in finding, particular variable stars or whatever it is, you'll get that alert. So I think we're going to want to find good ways to teach the public and have having a way to engage in that. And actually, one of the things that Rubin is about is this education and public outreach, and it was actually funded as a part of the construction by NSF. And it was actually one of the exciting parts of it because I don't think that had been done before on these major construction projects where you actually constructed some of the education and public outreach activities. So there is like a dedicated database for education purposes that the education and public outreach people are doing. And I'm actually not sure what they're going to do so I'm glad you're bringing this up, on what they're going to do to promote the alert stream. But one of the things is to connect to classrooms so that students can do stuff with the data. And, I think it would be kind of exciting for them to be able to ask that question. Well, how many are there? How many do you see? And in the early days when you're discovering things, how many new ones were found last night would be an interesting question to connect to the classroom. So,
I mean, there's a camera in the Netherlands that is in, I'm sure you've heard about this, was on the, this last week tonight, where it's in a dike or in a canal at a gate, and it is watching underwater for fish to show up. And there are thousands of people who are watching this camera, waiting for a fish to show up on the camera, that then they press a button that sends an alarm to the people who open up the gate to this canal, and then that lets the fish go through. And I think that the people who work on these instruments really underestimate the hunger and enthusiasm that the world will have for being able to watch this unfold in real time and be a part of some kind of larger picture, to connect to the science that's being done, because they are the taxpayers, they are the people that are helping to create this. And this is a way for them to then see the fruits of their labor. And I promise that they understand it. They get it. They want to be a part of this. And so, yeah, just, if there was like some kind of sphere of the universe and you could just like watch as supernova are popping off around the universe, or new, the moment new discoveries, or some way to visualize the science that is getting done, would be absolutely amazing. So that's just I'm telling you in advance,
Yeah.
the public would love this.
Well, that's great. I don't. I have to actually find out. A lot of times, I mean, I have a lot of things that we have to oversee, right? And right now we're just making sure we get get the thing
make
accurate
make it take pictures.
operations. So I
Yeah,
thought in a while about what they're going to do with the alert stream, because that it's an interesting thing. I mean, I know that we certainly want to make sure that the classrooms have access to the visuals so that they can go and explore, this universe and be able to zoom in on galaxies and really understand what's going on and have that kind of exploration. And it's, I think, really powerful to teach people like that. So those kinds of visual things are great, and they've been really good about making sure there's things that you can do on your phone, right? So that they work on the phone, on the web. And they have actually a little game you can play, like what is it like to bounce around the sky and do a survey. But I don't know if we've actually thought of a way to present in almost real time, right? Here's a supernova. It wouldn't. I don't think it would be too hard to show some of those things and the alerts. I just don't know if anybody's doing that yet. But it's
yeah.
great.
But I mean, even if the data are being put out and in these APIs that people can access and start to code their own layers on top of it, I think there's a lot of power there. If nobody is, I'll do my own, and then we'll do a live stream and with a extragalactic astronomer, and we'll talk about the different kinds of supernovae as they're happening. So one of the concerns that I know people have is light pollution, satellite trails. We've got the rise of the mega constellations, and Vera Rubin is one of the instruments that is going to be most affected by this. Where are we at in sort of concern, but also mitigation for satellite mega constellations with this observatory?
For me as an astronomer, satellites are not something new. The numbers we're talking about is so. What we've done in the past, right? So what I used to observe, right? You basically blank out the trail from your data, and that you don't have data there, but it's fine because usually we're taking multiple images. And here, this is the same case here. As we build up the entire picture of the sky, there'll be say 800 or so over the 10 years of every section of the sky. So you can imagine the ones with satellite trails crossed out. It doesn't really matter. You'll fill it in with lots of other data because things get rotated over the course of the 10 years. So the more satellite trails like that there are, basically it just becomes missing data. With Rubin's 10-year survey, if we have a lot of satellite trails that end up getting blanked out, we will stack the images together, build up the final image. And if we still think we need more data because there were a lot more satellite trails than planned, we can observe for another year if necessary, if we think that's going to help the ultimate legacy survey. So that's one of the things that can be done as a mitigation. You just observe a bit longer for the missing data.
Yeah, and I mean, you don't have to be concerned about whether or not you put Rubin into the right orbit, the way with James Webb. I mean, we've got a set time before it runs out of propellant, and then it starts to drift away, and then the mission is over. We saw that with Gaia. Rubin will always be on the right orbit. It's right there on planet Earth. And so I can't imagine that at the end of the 10 years, as long as everything's still operational, it won't just keep going.
Yeah, and and again, this is the kind of thing where the science will drive it, because what will happen, say 5 years from now, people will have some pretty good idea of what they would want to do after this legacy survey is done, and it could be that you're going to find, let's make some additional filters and do that because there might be some interest to do that. I don't really know. That could be one thing, or you're going to do the survey, do another survey where you have a different cadence, for optimized for different science. That could be where things go. It's really hard to say. So there's a lot of options, and that will play against do the satellite trails matter that much? Do we want to extend more, or just say, okay, that's enough and let's move on and do some other science? So the science will drive what those are. But I'll say, so that's one mitigation. You can just observe longer for the satellites. The other mitigation actually is one that's not so obvious because it's already built in. We don't know what the final anything looks like with Rubin as built, but along the line, everything is turning out to be better than planned, right? So it may end up we may be more efficient than originally planned, which means, that 10 years gets you a lot more than we had originally thought and need, as projected. So the mitigation for the satellites might not be that necessary. The 10 years will still be fine. So that's the other thing. But what we've been actively doing since around 2019, when we really started to understand what these impacts were going to be, we started working. The team started working with satellite companies like Starlink, and they've been very cooperative in trying to reduce the brightness of their satellites. And Starlink has kept their orbits, trying to keep actually lowering their orbits, which makes them a little brighter, but it also is a trade-off because then they're not visible for very long because they're closer to the Earth when they're on the dark side, at night. So, so those kinds of adjustments, and we'll just have to see what happens with other satellite companies. But certain things like that have helped, and so we'll see. Right at this point, we're not anticipating major impacts, but we have to keep working on these other satellite companies and see what we can do to reduce the brightness of the satellites and how much they're in and how long they're in the field.
Edward, the question I always ask people, what are you obsessed with right now?
What am I obsessed with? Well, I'm very excited to, cosmology has always been my area of greatest probably interest in astronomy and astrophysics, and so I'm very excited about the DESI results from Department of Energy and how Rubin is going to play into that. Right, it's going to be a very interesting time to see what ultimately that comes out to be. And as far as Rubin goes, it's going to be very exciting. So I'm excited about that, and I really am obsessed about what are these unknown things it's going to discover. So that's probably an area where I can't wait to see. But the more we learn about how the universe really originated, where it's going, that's just still the most fascinating question to me. Because years ago when I was young, it's like, well, we didn't know. Is it going to expand forever? Is it gonna collapse? And we're kind of, I don't want to say we're back to that, but we're in a territory where it's a little more uncertain again. And with like I said, if the DESI results hold, right, it's still in that statistical place where looking like it might be, but we can't be sure yet. Um, if they hold, then what the universe is, where it's really headed, is still not quite as clear as we might have thought, and so that's very exciting. But if you really want to be obsessed, right? As a physicist, I am not comfortable saying I don't know what 96% of the universe is, right? And that's where we are, right? And that story has gotten worse over my life, right? So that is not a comfortable place to be, and people seem to be very more comfortable than they ought to be, right?
Right, you want to find it.
Yeah. Well,
Yeah.
yeah. You want to be able to say what it is. That's one thing to say. We got these atoms and they're made up of electrons, neutrons, and protons. That's great. All right. And that's 4% of the universe. Okay. But all the things you see, yeah, that's all great. That's the stuff we know, but it's all the stuff we don't know that's driving everything. And that is not a comfortable, place as a physicist.
Well, good news. There's a powerful new observatory. It's just coming online. We should see first light by the end of this year, and that'll help answer some questions in that. Edward, thank you so much for taking the time to chat with me, and good luck with the continuation of the rollout and first light. I can't wait to see those first pictures.
We can't wait to show them to you. I can't wait to see them.
All right.
Thanks very much.
Thanks for your time. Bye-bye.
Bye now.
All right. I hope that brings you all up to speed on the state of Vera Rubin. And, it was a fascinating conversation with Dr. Edward Ajhar. Thanks to everyone at the National Science Foundation for making them available to me for this hour. And I will keep you posted, of course, as we learn more about this telescope. Now, I'm going to give you some final thoughts, but first, I'd like to thank our patrons. Thanks to Abe Kingston, Andrew M. Gross, Barry Lake Roofing, Brian Bodie, Caradwin, Chuck Hawkins, Commander Baylock, Cy Nielsen, David Gilton, David Matz, Dustin Cable, Evan Pro, Greg Feely, Hans Schultz, Hudson Ward, Jay Graves, James Clark, Jeremy Mattern, Jim Burke, Jordan Young, Josh Schultz, Marcel Smits, Michael Purcell, Modso, Paul Robach, Ren Kaidu, Robeck, Sean Sargent, Stephen Fowler-Munley, Vlad Shiplin, and Wolfgang Klotz, who support us at the Master of the Universe level. And all our patrons, all your support means the universe to us. All right, well, that's bucket list crossed off in the people that I want to interview. People always ask me, like, who do you want to interview? It's people like Edward Ajhar who are at, working day in, day out on missions, observatories, scientific discoveries. And so this was great to fill in a bunch of the gaps in my knowledge and to share that with you. And so, of course, we're going to be watching with bated breath as this instrument gets closer and closer to going to first light. And hopefully I will be able to find a bunch of interesting ways, representations that people are doing to share those data. And so you can watch as supernovae are discovered in real time, variable star information, new asteroids found, and of course, Planet Nine. And so one thing I'd like to hear from you is place your bets. Down in the comments down below, how many days after we get first light from Vera Rubin do you think that someone will announce the discovery of Planet Nine? I'd love to hear your thoughts in that in the comments down below. All right. Well, I hope you enjoyed this interview as much as I enjoyed conducting it, and we will see you next time.